Okay. So we're gonna start today by finishing off chapter 3. So let's start with section 3.5, and then we'll do the first section of chapter 4 after this. So this whole section is just going to be dealing with solving with equations that have the absolute value. So for example, say if we want to solve something like this one's number 11. The absolute value of 8x is equal to 24. So, we remember, maybe from like high school or something, the absolute value, what it does is that, like the absolute value of 3 is 3, but the absolute value of -3 is also 3 as well. So basically, if it's a positive number, it's just equal to itself. And if it's a negative number, you just get rid of the minus sign. So when you're solving these, let's just put this off to the side. Whenever you're solving an absolute value equation, like the absolute value of x is just equal to some number a, you're going to end up getting two equations you need to solve. Basically, what you have is x is going to be equal to a, and then also you're going to get x is equal to minus a. So in this situation, there's not too much to solve, but basically this x is just a placeholder. Whatever is on the inside, that's just going to go here, and it's also going to go here. So you'll have these two equations that you'll end up needing to solve. So if we take that idea and just put it over to this problem over here, number 11, what we have is, so 8x is going to be equal to 24. And 8x is going to be equal to minus 24. So you see that green box is just this 8x now. So 8x is going to be 24, and it also has to be minus 24. So if we solve that, on the left-hand side, just divide the 8 over, we get x is equal to 3. Divide the 8 over on the right, we get x is equal to minus 3. So we get two answers. All right, so say if we did 13, this one is saying x minus 1 is equal to 4. So now that green box that we have on the top right is the whole thing on the inside is x minus 1. So we're going to get x minus 1 is 4. X minus 1 is minus 4. So add the 1 over, we get x is equal to 5. Add the 1 over, we get x is equal to minus 3. What about 20? So 20 says 1/3 x minus 4 is equal to 13. So just like before, we're going to have the inside. So 1/3 x minus 4. So that's going to equal 13. And it's also going to equal minus 13. So just add the 4 over. We're going to get 1/3 x is equal to 17. Then we multiply by 3. So x is going to equal so 30 plus 21, 51. And over here, we add the 4 over. 1/3 x is equal to minus 7. Multiply by the 3, x is equal to minus 21. Oh, wait, did I make a mistake here? Should have minus 27. What's going on here? Oh, that's a 9. Sorry, this is a minus 9, not a minus 7. And this would make this a minus 27. Okay. Because when you add 4 over to the right-hand side, minus 13 plus 4 is minus 9, not minus 7. All right, how about, let's do one, so this, till we move on to a different, well, like 29. So 29 is basically the same problem, but there's just, we have to do some reorganizing before we solve this. So we have 12 minus the absolute value of x plus 6 is equal to 5. So if you look at above, like every problem that we had the absolute value on one side and then just a number on the other side. So we still need that set up. So we just need to get the absolute value on one side and everything else on the other side. So what we could do is subtract the 12 over, so we get minus the absolute value of x plus 6 is equal to 5 minus 12, which is minus 7. And then what we could do is divide by that minus sign. So the absolute value of x plus 6 is equal to positive 7. And then now basically we just turn this problem into just what we've been doing previously. So now the inside's x plus 6. So we're going to have x plus 6 is equal to 7. X plus 6 is equal to minus 7. So over here we get x is equal to 1. And then we get x is equal to minus 13. Okay, I think that's good enough for as far as, there's not many questions from this section. So that's basically the first half, like questions 1 through 32. And now the last half is going to be, so we just did equalities, but now we're going to change that. We'll do inequalities, like with greater than signs and stuff. So we have two different options for inequalities with absolute values. So we can do something like this, the absolute value of x. And then for these problems, it doesn't necessarily matter whether it's like a greater than sign or a greater than or equal to sign. For the most part, it's going to be, that doesn't change much. But we can have two separate problems here, like the absolute value being less than a number like this. Another option is going to be the absolute value is going to be bigger than some number. So on this left-hand side, what this ends up translating to is this. So basically whatever is on the inside of the absolute value, you just place it right here, and we basically sandwich it in between an a and a minus a. And on this one over here, what we have, this is going to mean these things. It's going to be x is going to be bigger than or equal to a, or x is going to be less than or equal to minus a. So these are whatever is inside of your absolute value. If it has like this type of setup, let's make this a little bit bigger. So if we have the absolute value being bigger than a number, just whatever's on the inside of the absolute value, we place it here, and then we place it here. And so notice these two things are different. This is saying x is bigger than a, and this is saying x is less than minus a. And this is saying x is in between minus a and a. So if we were like on a number line, let's make this a little bit smaller. So notice like on a number line, why these two things don't mean the same thing. So here's minus a and here's a. This one over here is saying x is in between minus a and a. So those are these numbers. But the one on the right-hand side, well, it's saying this is saying x is bigger than a, so that's over here. And then it's saying x is less than or equal to minus a, so that's over here. So notice that, actually, listen, let's not do, let's make this middle section, you can make it yellow. So this whole section over here, this is like the yellow section, and then this will be the red section. So you notice that these two things, they give us different things. So on the right-hand side, we have the red shading, but on the left-hand side, we have the yellow shading. Okay, let's do some problems with those. So we have, let's do just 33. Let's start with like a basic one. So here we want to solve the absolute value of x is less than 7. And so now basically how this setup is, well, it's on the top left. We have the absolute value being less than something. So all this means is we just do minus 7, less than x, less than positive 7. And in this particular problem, there's really nothing else to solve. So this is just going to be what this means. 41. So here we have 3x less than 1. So what this means is minus 1 less than 3x, which is less than 1. So then we can divide by the 3, so we get minus 1/3 is less than x, which is less than 1/3. Let's do 45. So in this one, we have the absolute value of x plus 8 is less than 9. And so it's still the same setup. The absolute value is less than something. So we're going to have minus 9, less than x plus 8, less than 9. Then we can subtract the 8 over, so we get minus 17. So minus 17 less than x, less than 1. So notice how what I meant by that sign, like this, it doesn't matter. It only doesn't matter in the sense that it's still the same thing, whether this is like a greater than or equal to sign or a greater than sign. If it's the absolute value less than something like this, then you just put that same sign over here. But if you see below how this is like a strict inequality sign, we just put strict inequality signs here. All right. Let's do 44, or no, it's forward. How about 48? So 48 is saying x plus 6 is bigger than 10. So this is now this top right version. So what this means is, well, the inside x plus 6 is going to be bigger than 10, or x plus 6 is going to be less than minus 10. So on the right-hand side, we have x is going to be bigger than 4. And over here, we have x is going to be less than minus 16. Um, 54. So x minus 7 is bigger than or equal to 0.4. So again, this is the situation where x, the absolute value is bigger than something. So we have the inside x minus 7. X minus 7 is going to be bigger than or equal to 0.4. Or x minus 7 is going to be less than or equal to minus 0.4. So over here, we can add the 7 over. So x is going to be bigger than or equal to 7.4. And over here, we add it over, we're going to get x is less than or equal to 6.6. Let's do 60. So we have 2x minus 1 divided by 3 is going to be bigger than or equal to 5 over 6. So it's still the same thing. We have the absolute value is bigger than that number. So 2x minus 1 over 3 bigger than or equal to 5 over 6. Or 2x minus 1 over 3 is less than or equal to minus 5 over 6. So on the left-hand side, let's solve that one first. We can multiply the 3 over. So we have 2x minus 1 is bigger than or equal to 5 over 2. And then we can add the 1 over. So 2x is bigger than or equal to 1 plus 5 over 2. Let's get a common denominator on the right-hand side. So that's going to be 2. So we can write that as 2 over 2 plus 5 over 2. So that's going to be 7 over 2. And then we are going to divide by that 2 over. So x is going to be bigger than or equal to 7 over 4. Let's see, it doesn't give us answer. Okay, so, oh, sorry, we need to do both sides. All right, so over here, let's multiply that 3 over. So we're going to have 2x minus 1 is less than or equal to minus 5 over 2. Then we add the 1 over, so 2x is going to be less than or equal to 1 minus 5 over 2. Then let's do our common denominator. 2x is less than or equal to 2 over 2 minus 5 over 2. And here we have 2x going to be less than or equal to minus 3 over 2. And then if we divide by the 2, we get x is less than or equal to minus 3 over 4. So then we have these two answers. Or this whole answer, but two parts to the answer. Okay, well, that takes care of all the homework questions. So there really isn't too many from this section. There's only just two types of problems, whether this is like an inequality sign or whether that's an equal sign. Okay, so let's do section 4.1. What do we have in here? Okay, So we're going to start with the, let's see. Let's just write something out just to kind of like, because we'll be using some words. Let's just write out their definition so you kind of know what we're talking about here. So say if we have a polynomial, which is something that just looks like this. So it's an x to the n, an minus 1 x to the n minus 1, a1 x plus a naught. So, and where these a values, they're just numbers, and x's, those are just our variables. So the only thing that we really need to talk about is two terms, or I guess one in general, is this term right here, the a n x to the n term. So a n x to the n is referred to, I don't know if I spelled that right. I don't think so. I think there's one F. I don't know. Maybe that looks worse. Is called the leading term. So if we say leading term, what that basically means is just the term that has the highest exponent. It is the term, not necessarily the term written first, but the term with the highest exponent, which in this part right here, the term with the highest exponent is the a n x to the n term. So it is the term with the largest exponent. Okay, I believe that's all we really needed. It's the only definition I think we need. Okay, so now we're going to have something called end behavior. And what end behavior is what's the graph? It's what the graph does for really big x values and really small y value, or really small. Sorry, I guess really positive x values and really negative x values. So it's basically what the graph does at like the end. It's probably better to draw a picture, but let's just write this down. It is what the graph looks like at, we'll say, plus infinity and minus infinity. So what we mean by that is, so for example, say if we have a graph right here, maybe goes down, so something like this, it does some squiggles in the middle, does that, doesn't really matter, and then it goes down over here. So the end behavior of this graph, all we care about is so what we say by like, here's plus infinities over here, minus infinities over here. So the end behavior is just going to be what happens at the very end. So at the very end, we see the graph just moves up forever. So on the left-hand side, that's what that end behavior does. And on the right-hand side, it just moves down forever. So this green section that we just drew, this is sort of the end behavior. Another way that we draw, so we could say, so for the above graph, we say the end behavior is, and there's a couple of ways to write this. So let's do the first way. The first way is just through a picture, and it's this. What this means, so for this above example, it just means on the left-hand side, it goes up, and on the right-hand side, it goes down. That's one way of writing it. Another way of writing it is going to be f of x goes down to minus infinity as x goes to infinity, and f of x goes to positive infinity as x goes to minus infinity. So you see what this means is f of x goes to minus infinity, so f of x goes down forever, as x goes to infinity, as we move over to the infinity side. In this bottom piece, f of x goes to positive infinity, see it goes up to infinity, as x moves to minus infinity, so as we move to the left-hand side. So both of these ways are the same, they mean the same thing. Mean the same thing. All right. And so how do we deter? So basically, just given a picture, it's easy to determine the end behavior. You just look at the left-hand side, look at the right-hand side, and see what it does. But for the most part, you're just given an equation. You want to know, okay, how can we find the end behavior? So let's do that. Finding end behavior given an equation. So all that matters is the leading term. So how do we write this? So let's just say, like, consider, say something like f of x is equal to an x to the n. We'll just rewrite that again. Plus a1 x to the 1 plus a naught. So we have our leading term right here. So remember, the leading term is the thing with the biggest exponent. Here's our leading term. So we're going to have 4 options for end behavior. And from this point on, I think it's just easier. Let's just do the graph notation. That requires kind of like less thinking, and we still get the same piece of information. So we have 4 separate options. Our first option is if an, so this is often referred to as the leading coefficient. It's just the number in front of the x to the m. So if an is positive and n is even. So this is option number 1. And so when this happens, the end behavior is going to look like this. So it's going to move up over here, and it's going to move up over here. So it basically means as we move over to the left, the graph just eventually moves up, and as we move to the right, the graph eventually moves up. Let's draw that a little bit better. So that's this end behavior. Number 2, if an is bigger than 0, but n is odd. So in this example, what happens is on the left-hand side, the graph moves down, and on the right-hand side, the graph moves up. Number 3 is if an is a negative number, n is even. Here we are going to have down and down. And then the last case, an is negative, n is odd. We are going to have it move up on the left-hand side and down on the right-hand side. So these are only the 4 types of end behavior. So for example, like questions 11 through 18 just says, what is the end behavior? And it gives you an equation. So let's just do a couple of those. Let's just make some up. That's probably easier. So say if we have, so let's give some instructions. So oh, we still need this. So for the following, state the end behavior. Okay, so for this first one, let's do f of x is equal to minus 7x to the 3 plus x. So here, what is our leading term? Our leading term, the thing with the biggest exponent, that is x to the 3. So we can say that our leading term is equal to minus 7 x to the 3. So in this situation, notice that we have a negative number in the front and the power is odd. So we our leading coefficient is negative. Let's see. Let's define that up above. So we have that whole thing as a leading term. Where can we squeeze this in here? Just so we have it like written down, we'll say an is the leading coefficient. So the whole thing's a leading term, and an is just going to be the leading coefficient. I think that's really all we need. So in this situation, we have our leading term is minus 7x to the 3. So our leading coefficient is minus 7, which is negative, and our power, which is 3, and this is odd. So we have to go, what is the, if you go back up to those charts above, what is the end behavior when we have a negative leading coefficient and an odd power. So that was right here. You see we have, or this bottom one, we have a negative leading coefficient and our power is odd. So when that's the case, that's our end behavior just looks like this. Goes up on the left and it goes down on the right. So the answer for this problem is it goes up on the left, goes down on the right. Okay, so what about for f of x is equal to minus 10 x to the 32 plus x to the 16 plus x. So here, our leading term is minus 10x to the 32. Minus 10x to the 32. Our leading coefficient is minus 10, which is negative. And then our power is 32, which is even. So if you go back up to the table above and you see, okay, which one has the negative leading coefficient and an even power, you'll see that our end behavior is going to go down on the left and down on the right. Okay, so how about f of x is equal to x plus x squared plus x cubed plus x to the 7. So here, okay, our leading term, the term that has the highest power is this x to the 7 term. Okay, so the number, our leading coefficient, the number in front of it is just 1, which is positive, and our power is 7, which is odd. So if you go back up to the above table, the thing that has a positive leading coefficient and an odd power, it goes down on the left and then up on the right. And then the last possible example we could have is, nope, okay, so f of x is equal to 33, x to the 10, plus x to the 8, plus x to the 7. So say for this one, we have our leading term is 33x to the 10, because x to the 10 is the biggest exponent. Our leading coefficient is 33, which is positive. And then the power of 10 is even. Okay, so what do we got here? We have a positive leading coefficient and a power that is even. So that means we're going to go up on the left and we're going to go up on the right. So these above 4 examples, these are the only types of examples we can have, which goes over those 4 cases that we talked about. So what else we got from this section? The last thing too, so basically this next bit, there's really nothing new from these questions. The only thing is something about the multiplicity. So, you know, we've solved equations. So maybe we never really talked about this word in particular. We can say a 0 of a function f of x is a value let's call that value, let's say a, such that f of a is equal to 0. So it's a number that we plug in and we get 0. And we can say we find them by solving no, there's no e there. By solving f of x is equal to 0. So you're just setting an equation equal to 0 and solving for x. Those values that we find, those things are called zeros. So we've done that before, like several times throughout this semester. The only thing we haven't talked about is multiplicity. And so multiplicity, so sometimes you know how we solve a function for 0 and we get the same answer twice. That means we'll have that multiplicity of times 2. So let's maybe the best way to talk about this is just by, or let's just write this down. We'll write it down in words and then we'll do it with examples. So the multiplicity of a 0. So let's say how can we say this in an easy way to understand? Let's say suppose a is a 0 of f of x. Also suppose when solving f of x is equal to 0, we get x equals a n times. Then the multiplicity of a is n. So the multiplicity of a is n. So what do we mean by that? So let's just do it with an example. Let's suppose we want to solve, or let's, just an easy example, something like x minus 3 cubed, or let's do squared. Is equal to 0. So what does this mean? Well, we could take the square. So when we're solving this equation, we have something squared is equal to a number. So we could just take the square root of both sides. So if we take the square root of the left-hand side, we just get x minus 3. So let's just do all that. So we could take the square root of x minus 3 squared, and then that's going to equal to plus minus the square root of 0. So over on the left-hand side, we just get the square root and the square goes away. So we just have x minus 3. On the right-hand side, the square root of 0 is just 0, but plus minus 0 mean the same thing. So it's just, sorry, no, this is actually not going to give us the, forget about this. Another way of, sorry, that was kind of confusing. Don't do the square root in this situation. So in this situation, what we want to do is, so we have x minus 3 squared is equal to 0. Another way of writing that is x minus 3, this is equal to 0. So we have like, 2 pieces equal to 0. And then, when we're in the situation, what we always do is just set each of those pieces equal to 0. So we get x minus 3 is equal to 0, x minus 3 is equal to 0. So over here, we get x is equal to 3. And over here, we also get x is equal to 3. So we see that 3 is a 0. We're solving for, what we're doing here, we're just solving this equation for x. We want to know what is the x value that we plug in and we get 0. Well, we do all this work and we see that we get x is equal to 3, and we see that x is equal to 3. So what this tells us is that 3 is a 0. Let's actually write x equals 3. So x equals 3 is a 0 of f of x, need some more room, is a 0 of f of x is equal to x minus 3 squared. If we plug 3 into here, we get 0. However, when we were solving that equation, we got x is equal to 3 twice. So that means it has a multiplicity of 2. X equals 3 has a multiplicity of 2, because we get x equals 3 twice when we're solving the equation f of x is equal to 0. All right, so let's do another example. How about something like 30. So what we're going to do is well, it's going to be the same for our, let's just write the instructions once. So let's say find the zeros and state their multiplicity. All right, so for 30, we have f of x is equal to x plus 1/2, x plus 7, x plus 7, and x plus 5. So find the zeros and state the multiplicity. So find the zeros just means set the equation equal to 0 and solve for x. So if we set this function equal to 0, we're going to get x plus 1/2, x plus 7, x plus 7, x plus 5 is equal to 0. And this function's already factored for us, so that's easy. All we have to do is just set each of the pieces equal to 0 now. So plus 1/2 is equal to 0. We get x plus 7 is equal to 0. X plus 7 is equal to 0. X plus 5 is equal to 0. On the left-hand one, we subtract the 1/2, so we get x is equal to minus 1/2. Here we get x is equal to minus 7. X is equal to minus 7. X is equal to minus 5. So here are all of our zeros. So our zeros, what we have are three unique, so just three separate zeros. We have x is minus 1/2, x is minus 7, and x is minus 5. So we have x is equal to minus 1/2, and the multiplicity is equal to 1, because there's only one of those. We have x is equal to minus 7, and the multiplicity is 2 because we have two of those. And we have x is equal to minus 5, and the multiplicity is 1 because we just have one of those. So you see there's 1x to the 1/2. We have 2x to the minus 7s, and then just 1x is equal to minus 5. Go up to 41. Okay, let's do 39. X cubed, 3x squared, minus x minus 3. So in this one, we need to factor, because we have to find the 0, so we need to solve this equation. So we need to solve this equation, so that means we need to factor the left-hand side. And this one we're going to do by group factoring. So notice on this first term, we can take out a x squared. So we're going to group these two together. We're going to group these two together. From this first term, we can take out an x squared, and we're left with a x plus 3. In the second two, we can take out a minus sign, and we're left with an x plus a 3. But now both of these terms have an x plus 3. There's an x plus 3 here. There's an x plus 3 here. So we could factor that piece out. So from the first term, we're going to be left with an x squared. And the second term, we're going to be left with a 1. And so now if we, have two pieces, set those pieces equal to 0. I guess one thing else we can do is we can continue factoring x squared minus 1. Let's do that. So this is going to be x plus 3. If we factor x squared minus 1, that's x plus 1, x minus 1. So that's equal to 0. Now we set all these pieces equal to 0. So we get x is equal to minus 3, x is equal to minus 1, x is equal to positive 1. So our zeros, we have x is equal to minus 3, and the multiplicity is 1 because we only got it one time. We have x is equal to minus 1. The multiplicity is also 1 because we only got it one time. And x is equal to positive 1. And that multiplicity is also 1. Let's see. Let's also do 35. So here, f of x, 35, is equal to minus 8 x minus 3 squared x plus 4 to the 3 and x to the 4. So we got to find the zeros of this and see, what are their multiplicities. So we need to solve this equation. So we have these pieces and they're all equal to 0. If you ever have a constant in the front, like a -8, that doesn't really matter here. So really when we're trying to solve for x, all we care about is that piece, and that piece. So we have these things all multiplied together, so we can set each of them equal to 0. So we have x minus 3 squared is equal to 0. We can solve x plus 4 to the 3 is equal to 0. And we can solve x to the 4 is equal to 0. So this left one on the right-hand side, so notice x minus 3 squared. So what does that mean? Well, that just means x minus 3 is equal to 0, which just tells us that x minus 3 is 0, x minus 3 is 0, which tells us we're going to get x equals 3, and also x equals 3. So notice we get 3 2 times, and that's always going to, because the power up here is 2. So if you notice, what this tells us is that we're going to get x equals 3, and the multiplicity of this one is going to be equal to 2. If we solve this one equal to 0, we're just going to get x plus 4. So we would get this. X plus 4 is equal to 0, but we're going to get that 3 separate times because that's a cubed up here. So we would just write that out 3 different times. But just to save time, we don't need to do that. So with this one, we're going to get x is equal to minus 4 with our multiplicity equal to 3. Over here, we have x to the 4 is equal to 0. That's just the same thing as writing, x is equal to 0, x is equal to 0, 4 separate times because we have a power of 4. So really all we're doing is we're solving this equation 4 separate times. But there's nothing to solve here. We just get x is equal to 0. So that's our 0, and our multiplicity is going to be 4. Okay, that actually takes care of all the problems from this section too. All right, yeah, so that's good for the day. I'll post the chapter 4 homework online. Actually, no, I already did that. I'll make a submission link for it though. Okay, cool. Thank you, and I'll see you guys tomorrow.